Hello. We're going to be talking about section 11.2 today, complex numbers. So first of all, in order to talk about a complex number, I need to introduce the idea of an imaginary number. An imaginary number is a number that includes I. And we're going to define I to be equal to the square root of -1, which I'll be talking about a little bit later. So the number I is called an imaginary unit. And when I put numbers in the form of a plus bi, I call them complex numbers. These are numbers that are going to look like 4 plus or minus 5i, where 4 is my real part and the 5i is my imaginary part. So I have a real number plus or minus an imaginary number, and we call those complex numbers. Basically, all the numbers you've worked with are complex numbers because you could think of the number 4 that you're used to working with in your math problems as being 4 plus 0i. 0 times i would be 0. You could think of an imaginary number such as 5i, which you're going to begin working with. You can think of 5i as really being 0 plus 5i. So then it's also a complex number. So a complex number refers to a real part and an imaginary part. An imaginary number refers just to a number that includes an I, or 1 times I. So on the next part, you see where we have defined some values for I with exponents. Begins with I to the 0 power being 1. Anything to the 0 power is 1. You've seen that before, so that makes sense. And then I to the first power would be I. Well, most things to the first power. 5 to the first power is 5. -2 to the first power is -2. X to the first power is x. So that makes sense. But now we get to the I squared equals -1. This is new. This is what you'll need to accept to be able to do your work today. Since I squared equals -1, I squared equals -1, when we take the square root of both sides, you'll see that the square root of I squared would be I. And that's why we're saying that I equals the square root of -1. So today, when we have square roots of negative numbers, we're finally going to be able to have an answer for that. So I cubed goes on to say is equal to -1. The way we start getting at multiple powers of I is we break them down. I can think of I cubed as I squared times I to the first, where I would add the 2 plus 1 to get the 3, going back to unit 2. So that would mean that I squared is -1, I first is I, so then it makes sense that I cubed then would be -I. The same way as we break down I to the fourth. I to the fourth can be thought of as I squared times I squared, where 2 plus 2 would be my I to the fourth. Well, we know that I squared is -1 because we're going to accept that. And then -1 times another -1 would be a +1. We can continue breaking down powers of I as they go up. We can define I to the fifth by breaking it into I to the fourth times I, and we're going to find that we get I when we do this. I to the sixth will be -1, I to the seventh will be -I, and I to the eighth will be 1. I can continue this pattern. If you break down I to the ninth, you're going to find that you're going to end up getting I for the final answer. I to the 10th will be -1 again. I to the 11th will be -I. And I to the 12th will be 1. So this is a pattern that we're noticing is being created, a pattern by 4s. It's a cycle. So this is how we can figure out powers of I. We can use the fact that it goes in this pattern by 4s. So sometimes you want to figure out I to an exponent that's larger. You don't want to start breaking that down into smaller values of I to another exponent. Instead, we can use a shortcut. We can divide, D-I-V-I-D-I-N-G. We can divide the power by 4. So in this case, we can find where on the cycle this exponent would be. So if I divide 22 by 4, I would get a remainder of 2. This is telling me that if I look at my cycle going by 4, that I to the 22nd would be in the same column as I squared. So I know that I to the 22nd is equal to I squared, which we learned was -1. We can do the same thing for I to the 17th. We just need to find what place in the pattern I to the 17th would be. So let's divide 17 by 4 and see what our remainder is. Our remainder is 1. That means I to the 17th would be in the same place in our pattern as I to the 1st. So I to the 17th equals I to the 1st, which if you look at the other side, we know that that's I, anything to the first power. So this is how I can break down larger powers of I. So you'll primarily be using this to do square roots of negative numbers. So for example, if we have the square root of a number, we can pull out of a negative number, we can pull out the -1 because I know the square root of -1 is equal to I. So in this case, if I'm looking at the square root of -16, I can think about the square root of -16 as being the square root of -1 times 16. So the square root of -1 is I, and the square root of 16 is 4. So generally we write the numerical number first, in this case the 4, and we write the I second. We would write 4I. We wouldn't write I4. You'll notice I didn't put a plus minus here. That's because this square root is not in a quadratic equation. The moment I change this to be x squared equals the square root of -16, I'm sorry, I shouldn't have put the negative there. Pretend the negative's not there. I'm sorry, the square root symbol. If I had x squared equals -16, I would take the square root of both sides, and I would get x equals. Now that I have a quadratic equation, I know that the square root of 16 would give me a plus or minus 4. So now I think about the 16 as giving me the plus or minus 4, and the -1 giving me the I. So the square root of -16 would indeed be plus or minus 4I. However, this is not inside of a quadratic equation, and the square root of 16 is 4. So ladies and gentlemen, let's look at a square root that doesn't reduce. 70 is simplified. You could think of 70 as 2 times 35, which is 2 times 5 times 7. There's no perfect squares when you factor 70. So in this case, I would think of the square root of 70 as simply the square root of -1 times 70, where I can take the square root of -1. The square root of -1 is I. So I'm going to pull that out in front of my square root, and I'm going to leave the 70 underneath. And that would be the simplified answer for that problem. And finally, on this page, we're going to look at the square root of -48. So 48 does simplify. 48 can be thought of as 16 times 3. So in this case, the square root of -48 equals the square root of -1 times 48. If in my mind I want to think about that as the square root of -1 times 16 times 3, I now can take the square root of -1, that will be an I on the outside. I can take the square root of 16, that will be a 4 on the outside. And I still have a 3 left on the inside. If you're having a lot of trouble breaking down 48 and getting 4 square root of 3 for the 48 part of it, that was unit 2, and I'd be happy to help you with that during office hours. Notice I don't have a plus minus in front. Again, that's because this was not in a quadratic equation. The moment I solve a quadratic equation, I will put a plus minus in front of my 4. So flipping to the back side of your notes, we have some examples of square roots. So on these examples, I have the square root of -121. 121 is a perfect square. It's the square of 11. So in this case, I could think about this as the square root of -1 times 121, where the square root of -1 is I, and the square root of 121 is 11. You would write the 11 in front of the I. If this was in a quadratic equation, if you came down to x squared equals -121, and you took the square root of both sides, you would write this as x equals the square root of negative 1 is I, the square root of 121 is 11, but since I'm in a quadratic equation, it would be plus or minus 11. I don't want to confuse anyone with this part. The square root of 121 is 11. It always has been, it always will be. But when I'm solving a quadratic equation, I'm trying to figure out what x could have been. X could have been a positive 11i, or x could have been a negative 11i. Going down to this problem, 120 is always fun. 120 simplifies in lots of different ways, but the quickest way to simplify this one is if you think about it as 4 times 30. 30 is 5 times 6. There's no perfect squares there. So I can take the square root of the negative. That gives me an I. The square root of 4 is 2. And then 30 would stay underneath my radical symbol. And you would have the number in front, the I after it, and then the remainder of the square root behind. And this is how we would simplify the square root of a negative number. So sometimes we need to be able to handle operations such as addition, subtraction, and multiplication of complex numbers. In this situation, the I works very much like a variable, but keep in mind it's not. The I is not like an X or an A or a B. I is an imaginary number. This is a complex number. This is the real part. This is the imaginary part. This is the real part. This is the imaginary part. So to add these, you simply add like terms. If you want to think about it that way, I put it in parentheses because really I'm adding my real numbers and I'm adding my imaginary numbers. So in this case, I would add my 3 plus negative 2. That would give me a 1. And then I would add my negative 4i plus my 6i, and that would give me 2i. My answer would be a complex number where I would write the real part first and the imaginary part second. I would add my real parts and add my imaginary parts to get my final answer of 1 plus 2i. What about subtracting? Here's where commonly in the beginning some mistakes are made. You need to remember to distribute the negative to every number. So I need to remember to distribute this negative to both terms in the parentheses. This is really negative 4i plus 3i, negative 4. Sorry about that. Plus 3i, and then I get a negative 6 and a positive 7i. Again, I'm going to combine my real parts, and then I'm going to combine my imaginary parts. So in this case, the negative 4 and the negative 6 would give me a negative 10, and the positive 3i and the positive 7i would give me a plus 10i. This is my real part, this is my imaginary part, and negative 10 plus 10i is a complex number. So when we multiply complex numbers, I multiply them just like we learned to multiply binomials in Unit 2. So you're going to use box or FOIL method here. So let's do this one with box method since so many people in our class prefer that method. So I have 2 and negative 3i across the top, so I'll put the 3 and the 4i across the side. 3 times 2 is 6. 3 times negative 3i is negative 9i. 2 times 4i is 8i. And 4i times negative 3i would be negative 12i squared. I'm going to do something with that term in just a moment. So let's write down what we have in our box, and as I do that, I am going to combine my 8i and my negative 9i along the diagonal, and I'm going to get 6 minus I minus 12i squared. However, unlike when you've been doing binomials times binomials, I can't really have an I squared because I know what I squared is equal to. I squared is equal to a negative 1. So this is really 6 minus I minus 12 times a negative 1, which negative 12 times a negative 1 would be a negative 12, would be a positive 12. So I really have 6 minus I plus 12, and since 6 and 12 are like terms, to finish this problem off, I'm going to add them together, and I'm going to get 18 minus I for my final answer. Do not leave an answer with an I squared in it, because that's not simplified. Let's take a look at our example 5. This is multiplying again. This is the situation where you have to remember to write it twice. Some of you guys like to just square this and call it a day, but we don't want to get a wrong answer. So since I used box method last time, I'm going to use FOIL this time. So my first terms would be 4 times 4, or 16. My inner term would give me a plus 12i. My outer term would give me another plus 12i. And my last terms would then give me my 9i squared. So at this time, I'm going to combine my two like terms. This was a 12, I apologize. 12i and 12i, and I get plus 24i. And then this 9i squared is not simplified because I know that I squared is really equal to negative 1. This is 16 plus 24i plus 9 times negative 1, which I know is negative 9. So really, I'm looking at 16 plus 24i minus 9. Since the 16 and the minus 9 are like terms, I'll go ahead and combine them, and it's 7 plus 24i. Notice in this problem and the last problem, I wrote the real part 7 first, and I wrote the imaginary part second, which is the 24i, and this is my complex number. If I could put example, I guess I have two example 5s. If I could put the previous example back up, notice again I have my real part and my imaginary part, and 18 minus I is my complex number. So our final example is one that comes up whenever I multiply conjugates. Conjugates are what happens when I have the same numbers, but I put a plus sign and minus sign inside my binomials. You might remember these from our Unit 3A and our Unit 2. When this happens, our inner and outer terms cancel. The same thing happens with complex conjugates. In this case, these are complex numbers. I have a real and imaginary part that match the real and the imaginary part, but the difference is my signs. So I'm going to go ahead and set up box method for this one. And I have my 6 plus 5i we'll put across the top, and 6 minus 5i down the side. My 6 times 6 would give me 36, 6 times 5 would give me 30i, and 6 times negative 5 would give me negative 30i, and negative 5 times a positive 5i would give me negative 25i squared, which we all know we're going to have to simplify. But notice on my diagonal, my negative 30i and my positive 30 do cancel, and I expected that because of my matching parts, and the only difference was my signs. So this is equal to 36 minus 25i. This is I squared. This is where the interesting thing happens with complex conjugates. Since my I terms canceled and I have an I squared, I know that's negative 1. So this is really 36 minus 25 times a negative 1. So it's really 36 plus 25. And interestingly enough, when I get done, I only have my real number part of my complex number. I only have the 61. So when you multiply two complex conjugates, you'll notice that your answer is going to be a real number. Pretty interesting. So these would be the notes for 11.2, operations with complex numbers. We've learned to simplify I to high exponents. We've learned how to handle square roots of negative numbers, and we've learned how to add, subtract, and multiply complex numbers. You should be able to do the homework assignment for 11.2 at this time. Thank you.